Good evening, sir. Yes, sir. You're audible.
Good evening. So in the previous lecture, basically we discussed Ree's lemma, and Ree's lemma is basically related to the quotient spaces because we are considering the distance norm for the subspaces. So X is a nonlinear space and Y is a proper closed subspace of X. And if we have any number between 0 and 1 R, then there exists a corresponding unit vector xr such that distance of xr with the subspace is in between r and 1. The value of the distance is between r and 1. So this is so kind of if we have any number between 0 and 1, then we have the vector xr such that this distance of xr with y will come here in this interval. Okay, so this result we have seen one application of this result. So mainly this result we proved using the properties of the quotient norm as well as the property of infimum, and then we discuss one application that when the closed unit ball becomes compact set. So usually if we have a nonlinear space x equals to R2, and in which if we take Euclidean distance, that is basically the Euclidean norm, corresponding norm is Euclidean norm, then the closed unit ball is nothing but the closed unit disk, and that we know it is always a compact set, right? If x equals to capital X equals to R2 and usual norm we take Euclidean norm, then the closed unit ball is compact. But in general, this is not true for every nonlinear space. So that is this result, that every closed and bounded subset of nonlinear space is compact if and only if closed unit ball is compact, if and only if the nonlinear space is finite dimensional. The nonlinear space is finite dimensional. Yeah. So in this case, yeah, so we proved 1 implies 2, that is just trivial because we know that closed unit wall is closed and bounded set, and then we proved 2 implies 3 using the Rees lemma, and then we were discussing 3 implies 1. So in 3 implies 1, so third condition is basically that x is finite dimensional. Uh, yeah, so that is our assumption, and what we want to prove is that every closed and bounded subset of the nonlinear space is compact. So since X is m dimensional, we have considered the basis y1, y2, ym of X, and since X is m dimensional, we have started with any closed and bounded subset of X. We want to prove that this closed and bounded subset is compact. So since E is a subset of X and X is already finite dimensional, so E is already bounded, right? So to show it is compact subset of a matrix space. So we know that if we have any subset of a matrix space, we want to show it is a compact, we need to prove two things. First thing is it is bounded, second thing is it is closed, right? Yeah, so that is the thing we want to prove. Other thing, equivalent condition is that is compact. To prove that in metric space, we need to prove that every sequence has a convergent subsequence. So that is what we will prove here. To show it is compact, we will show that every sequence in E has a convergent subsequence. So xn is a sequence in E and E is bounded. So therefore xn itself is a bounded sequence. And then by our known result that if xn is bounded and xn is element of finite dimensional space, we will get corresponding coordinate sequences. So this is first coordinate sequence, second coordinate sequence, mth coordinate sequence corresponding to given sequence. And since xn is bounded, each of these sequences are bounded for every j. So this one result we have discussed that if we have xn is a bounded sequence of a finite dimensional vector space, then each coordinate sequence is bounded. And if xn is a convergent sequence in a finite dimensional nonlinear space, then each coordinate sequence is convergent. So here we are discussing the boundedness part of that result, that xn is bounded implies k and j is bounded, and k and j is a sequence of scalars. And for scalars, we can use the Bolzano-Weierstrass theorem. So Bolzano-Weierstrass theorem says that if you have a bounded sequence of a scalars, then either real numbers or complex numbers, then it will always has a convergent subsequence. So now these are m sequences, right? Kn1, Kn2, Knm. So if we apply Bolzano-Weierstrass theorem, what we get is we get a for j equals to 1, we get a sequence, subsequence. Right. So this we have written here, but I have not explained. So in the last step, since Kn1 is a bounded sequence in K by Bolzano-Weierstrass theorem, so this every bounded sequence has a convergent sequence. So let us say this sequence is K and K. Yes, K we already used. So let us say KNL 1. So this is a subsequence of this sequence and it is convergent. K and 1. Right, so it is a convergence sequence of the first sequence, first coordinate sequence. But what we want is we want a common subsequence for each j. So for that, what we'll do, we have already one subsequence. From those terms of this subsequence, we will select another subsequence such that a and m2 is convergent. Right. So from the terms of Kn, what was that? KNL1. Yeah, so basically what we are saying is since Kn2 is a convergent sequence, the subsequence was the coordinates? Coordinates are KNL 2. So this is a subsequence of this second coordinate sequence. Right. So we are not taking all the terms of the sequence. We are only taking the terms which corresponding to this subsequence. So since the original sequence is convergent, we know the result from real analysis that if the sequence is convergent, every subsequence is convergent. So this subsequence is also convergent. Oh, sorry, this is bounded, right? So that is our assumption that each of the K and J is a bounded sequence. Xn is bounded, each of this is bounded. So each of this is bounded, so every subsequence is bounded. And now again applying Bolzano Weierstrass theorem. This subsequence has another subsequence which is convergent. So this is a bounded sequence, its subsequence is we get a subsequence KNM2 which is convergent. Now this subsequence, we have the corresponding subsequence of the first coordinate. Note that KNM1 is a subsequence of the first sequence. So first sequence is KNL1, and therefore it is convergent, right? Because this subsequence is a subsequence of this, and this is already convergent, so this is convergent. What we got is we got the terms NM for which both first and second subsequence is convergent, right? So now repeating like this, we can construct a common subsequence. So we can construct subsequences. So let us call it K and P M J, such that each subsequence is convergent for J is equals to 1 to up to M, right? So each of the M coordinates sequences has a convergent subsequence, and then we know we will use the reverse result. So earlier we used that Xn is convergent, then each coordinate sequence is convergent, right? Bounded implies bounded, but now we are using convergent implies convergent. So each of these is convergent, so therefore X and P is a convergent subsequence. So from where we started from assuming that Xn is any sequence in E, right? we started with xn is any sequence in E, and then we proved that it has a convergent subsequence. So that is a sequential compactness. So therefore X is sequentially compact, and therefore X is compact. So sequentially compact, that means every closed and bounded, so not X is sequentially compact, and every closed and bounded subset E of X is compact whenever X is finite dimensional. Finite dimensional, basically this is compactness and sequential compactness are equivalent condition. So what is the application of this result? This result says that X is a nonlinear space, and in that nonlinear space, when the closed unit ball is compact. Right. So if we take infinite dimensional vectors nonlinear space, then by default it's, I mean, as an application of this result, the closed unit ball is not compact in the infinite dimensional vector space, nonlinear space. So we have studied infinite dimensional nonlinear spaces. Those are L1, L2, L infinity, the set of all polynomials. All of them are infinite dimensional nonlinear spaces. Now, you may have come across the notion of stronger and weaker topology. So every metric space or a nonlinear space, also we can compare the norms, and we can say that one metric space is weaker than the other metric space, or it is stronger than the other metric space. So for that we need to compare the metric, or we need to compare the convergence of the sequence. So let us compare. Comparison of different norms on the same vector space X. So if we have a vector space X, and if we have two norms defined on that, so first we are defining this norm on X, and that corresponding metric is dxy is equals to norm of X minus y. Right, norm is the same, and over the same vector space X we are defining dash norm. Right, so this dash norm will give another matrix. Let us call it d dash. So d dash of X with y is nothing but X minus y dash. So either we say the norm linear space is stronger, or metric space, corresponding metric space is stronger, depending on convergence of sequence. So the definition is that we say that the first norm is stronger than the second norm, dash norm, if every sequence xn in the norm with elements from the nonlinear space X, whenever xn converges to X, implies so xn converges to X in the first norm, implies xn converges to X in the second norm. So what does this mean? This means that we say that first norm is stronger than the second norm if so xn converges to X in the first norm means xn minus X converges to 0, right, as n tends to infinity, implies xn converges to X in the second norm dash norm as n tends to infinity. So this is regarding stronger. So if the first norm is stronger than the second norm is weaker than the first norm. In this case, we say that the second dash norm is weaker than the first norm. Right, so nonlinear space is same, but vector space is same. We are just changing the norm, two norms on the same space. We can define two norms on the same vector space. If we recall that we have defined one norm, two norm, and infinity norm in R2, right, in Rn also. So over the same vector space, we can define different norms, and then we can compare them. So what this says is that whenever xn converges to X in the nonlinear space X with the first norm, xn will always converge to X in the second, in the dash norm. Right, so therefore it is a stronger convergence, stronger condition. So this condition has an equivalent form. So let X be a vector space so the norm is stronger than the second norm if and only if the second norm dash norm is less than or equals to alpha times the first norm for every element X in X. If this condition is satisfied, then that condition is equivalent to saying that the first norm is stronger than the second norm. Yeah, so this will be related to continuity of linear function. We will discuss it in the later part of this talk, how this is related to continuous functions. So first let us try to prove this result. Yeah, so to discuss the strongness, we need to just check this condition. Right, xn converges to X in the first norm implies xn converges to xn in the weaker norm. So let us try to prove first prove this the converse, which is quite trivial. So if let us call this star condition. So suppose star holds, right, star is satisfied. If star is satisfied and we want to show the first norm is stronger than the other one, so that means xn converges to X in the first norm implies xn converges to X in the second norm. So suppose star holds, then xn converges to x in the first norm implies if you use this, what happens? Norm of xn minus x dash norm. So we are just substituting instead of x xn minus x. So we get this is less than equal to alpha times xn minus x. Right? Just substituting instead of x xn minus x. So star has given this one, and then we know this converges to 0. Second term converges to 0, right? So alpha times that term will also converge to 0. So therefore we get xn minus x dash converges to 0 because this is always non-negative, right? 0 less than equals to this term, which is less than equals to the term which converges to 0. So therefore xn converges to x in the dash norm. So starting with this condition, we got the other condition of the strongness. So therefore the first norm is stronger than the second norm. So we just use the star condition and the convergence of sequence. Yeah. So here it is not mentioned, but what is alpha? Alpha is some fixed positive number, right? So alpha is some fixed positive number for which norm x dash is less than equal to alpha times norm x for every x in x. Okay, now the converse of the converse, that means the forward condition. So if first norm is stronger than the other norm, then we want to show that there exists some alpha, right? There exists some alpha so that norm x dash less than equals to alpha times norm x. So suppose there does not exist any alpha, right? So we are assuming the conclusion is false, right? So suppose there does not exist any alpha greater than 0 such that norm of x dash is less than or equals to alpha norm x for all x in x. So suppose this statement is false. So that does not hold. Basically, that is what we want to say. So now we need to write down the negation of this. So that means for every alpha greater than 0, there exists x depending on alpha so that this is strictly greater than this one, or some x alpha belongs to x, right? Depending on what alpha is given. So in particular, if we choose alpha depending on natural numbers, so then for every natural number we'll get xn, right? So in particular, take alpha is equals to natural number. So therefore, for every natural number n, there exists xn belongs to x such that this condition for alpha equals to n. So that is xn dash greater than n times norm of xn. Right. So this we got by the negation of the statement, and then we know that norm of any vector is a positive number. So clearly xn cannot be 0. Why? Because if xn is 0, then this term is 0 and this term is also 0. So we get 0 less than 0. So that is a contradiction. Note that xn is not 0, right, for every n. So if xn is not 0, that means norm of xn is non-zero. So therefore we get, so since norm of xn is non-zero, we can divide this inequality by norm xn. If we divide this inequality of norm xn, we get norm of xn divided by n times norm xn. Its dash norm is greater than 1 for every n. Right. So these elements, whatever we obtain, xn divided by n xn and norm xn, we call them yn. Right. So let us call yn the elements which is xn by n times norm xn. Right. So then what we get is we get norm of yn, which is norm of yn dash. In the dash norm, these terms will be greater than 1 for every n belongs to n. Right. But on the other hand, what is the first norm of yn? So that is first norm of xn divided by n times norm xn, and then we know that if we take 1 by n common, this is norm xn by norm xn, that is 1. So yn has norm 1 by n that converges to 0 as n approaches to infinity. Right. So what we got is yn converges to 0 in the first norm, but yn does not converge in the second norm. Why? Because yn dash is greater than 1 for all n belongs to n. Right. So yn converges to y, but yn does not converge to essentially 0 in the dash norm. Yn does not converge to 0. In the second norm. So therefore the convergence is not strong. So therefore this norm is not stronger than the second norm, which is a contradiction. So this contradiction arises from our assumption that that alpha condition, star condition is false. Right? So therefore star condition holds. This condition holds. So therefore the convergence of sequence, the stronger condition of this, that to verify that we need to verify only the star condition. So that is the theorem. So why this theorem is important? Because we know that on R2 we have 3 norms defined on R2. Right. So all these three norms, R2 or Kn, let us say. So with respect to these norms, whether we can say that every sequence Xn converges to X converges in each of these norm or not. So example. So recall that on Kn means n coordinates, we have defined three norms. So what are the norms? Norm is first norm, second norm, and infinity norm. So which of these norm is stronger than the other? So I will discuss some of the comparison, all of them. The other comparison I will give as an exercise. So suppose we want to compare the first norm with the second norm. Right. So let us first write down what are these norms. So let x1, x2, xn be an element of Kn. Then yes, x, this is x element. So then what is the first norm of X? Yeah, so can anyone say that what is the first norm? So this is basically Rn. When K is R, this is Rn. So Rn, what is the first norm which we discuss?
So it will consist of all those sequences which are whose summation is less than infinity.
This is not a sequence. These are the coordinates. Rn. I'm saying
Okay,
this is
sir.
not a sequence space. Yeah.
Then it will consist of x such that summation of from j equals to 1 to infinity such that x of j is less than infinity.
J is equals to 1 to n xj. This is a finite sum. This is always convergent.
Sir, from j equals it x such that summation from j equals to 1 to infinity, x of j is less than infinity. Summation is less than infinity, sir. I am taking summation from 1 to infinity, sir.
See, first you understand which space you belong to, right? You are not taking sequences, so you should not talk about series. Okay, so what I am saying is here we are taking only n coordinates, 1, 2, 3 up to n. So if you add n coordinates, it will be always finite number. It can never be infinite. Right? And second thing is we are taking norm. So norm cannot be negative. This number can be negative. So therefore we need to take here modulus. So this is the first norm. Second norm is what? Again, summation j is equals to 1 to n, the Euclidean norm. So that is modulus of xj square. Right? In Euclidean norm, we take square. And we need to take its square root. Fine. So this is Euclidean norm. And the third norm is infinity norm. And here we have only finitely many coordinates. So instead of supremum, because only n coordinates are there, it is a maximum of x1, x2, xn, right? And again, this is a norm. The numbers can be negative, norm cannot be negative, so therefore we need to take modulus. Right, so these are the norms which we have considered. And when we take, instead of n coordinates, if we take sequences x1, x2, xn, so on, then here we take up to infinity, right? Infinity, and here also. But we are not taking that, we are only taking finitely many coordinates. So what is going on, just try to understand. Otherwise, the course will complete and you will not gain any knowledge. Right? So you see some examples, read some books. Okay, so these are the norms, and yeah. So what is the question? Question is that we need to find which norm is stronger than the other norm. So for that, this condition will be used. Star condition will be used. So to verify the star condition, what we need to do? We need to first choose two norms, and we need to find some positive number alpha, right? So for every two norms, the question is whether we can find alpha. If we can find alpha, then the second norm is stronger than the first norm, right? That is what is this statement. Okay, so here it is very simple because we have only n coordinates. The sequence is also, it is simple, but it involves some analysis, real analysis, because we have a convergence of series there. Here we don't have convergence of series. We just have sum of the numbers and numbers. So let us start with comparing the two norm with the first norm. So if we start the first norm x1, so x1 we know that that is modulus of x1 plus modulus of x2 modulus of xn, right? The question is, can we find this is less than equals to alpha times 2 norm, right? So what is alpha times 2 norm? 2 norm is basically square root of x first coordinates modulus square plus second coordinate modulus square, nth coordinate modulus square, right? So can we find some alpha so that this number is less than equals to square root of this number? So there we will need some inequality. So if you recall inequality, we have an inequality that xj yj modulus. What is the Cauchy square inequality? This is less than equals to x1 square plus x2 square xn square, right, times square root of y1 square y2 square yn square. So this Cauchy square inequality, if you use for this number, then what will be alpha? Yes, what will be alpha? Tell me. Yeah, yes. Am I audible?
Yes, sir, you are audible.
Yeah, so if we take the modulus of x1 plus modulus x2 plus modulus xn, if we apply Cauchy-Squarz inequality, what we get instead of this square root modulus y1 square, y2 square, so on.
Under root n.
Right, so that will be square root n because we are actually comparing this one with this term. Right, so we are taking yj to be 0 or yj to be 1. Each yj is 1, that means the square root of 1 plus 1 plus 1 n times. So that is square root n. So what he said is correct, that should be square root n. So this is less than equals to square root n times. What is this? This is just 2 norm of x. So that is what we got here, that alpha is root n. Right. So such a number exists. Now why alpha is root n? Because n is fixed here. We are considering n coordinates. Right? We are considering n coordinates. So n is fixed. We are in Rn. If we are in R2, 2 is fixed. Okay. So since this holds, the reason is Cauchy-Squarz inequality. Okay, so basically each yj we are taking to be 1. So that gives this inequality. So that means the 2 norm is stronger than 1 norm on Kn. Right. So this is the comparison of 2 norm with 1 norm. So similarly, 1 norm with 2 norm also we can compare. On the other hand, if you take the 2 norm of x, then what is the 2 norm? 2 norm is basically modulus of x1 square, x2 square, xk square, xn square. Right. So we have a Euclidean norm. So can we find this is less than equals to alpha times sup norm? So we know that sup norm is nothing but maximum of modulus of x1 modulus of x2 xn. So, so in this case, what will be alpha? Just try for 2. So suppose we have mod x1 square plus mod x2 square. Can we have it alpha times maximum of mod x1 mod x2? If that is true, what is alpha? Now this is a very simple question. You are studying optimization. Yeah, Anurag, any idea about this? How, what will be the value of alpha? Anurag,
Yes, sir.
yeah, so if we want to find alpha such that square root mod x1 square plus mod x2 square less than equals to alpha times maximum of mod x1 mod x2, then what will be the choice of alpha? Okay, so basically we are using this thing, right? So x1 is always less than equals to maximum of, right? So that means its square is also less than equal to square of this. Similarly, x2 square is always less than equals to maximum of mod x1 mod x2 square. Now you add this, so we get x1 square plus x2 square is less than equals to 2 times maximum of square. And then now you take square root. So this is square root times square root of this. That is root 2 times maximum of so what is alpha? Alpha is 2. Alpha is root 2. Right. So one of the choices alpha is root 2. So this is less than equals to. So what will be here? Here it will not be root 2 because there are n coordinates. So that will be root n times maximum of x1, x2, xn. Right. So basically we are using just the comparison of real numbers. It's maximal comparing with maximum value and so on. So I believe these things you already know, but only we are reframing it. The comparison of these numbers you already know. Only thing is this norm comparison we are doing first time. So what we done is we compared 2 norm with the infinity norm. So therefore, this norm is stronger than the 2 norm on Kn. So in short, what we have done is x1 is less than equals to, what we proved is basically x1 is less than or equals to root n times 2 norm of x, and then we proved 2 norm of x is again root n times infinity norm, right? So therefore we got the 1 norm less than equals to root n 2 norms less than equals to n times infinity norm. So this is true for all x in Kn. Now the converse. So here we written x, this one is stronger than this one is stronger than this, so obviously this one is stronger than this one. Now the other way around, so whether x1 is stronger than x2 and whether x infinity is stronger than sorry, the other way around, so whether x1 is stronger than x2 and whether x1 is stronger than x infinity. Right, so for that we have that part I will give as an exercise. So verify that the infinity norm of x is less than or equals to 2 norm of x less than or equals to 1 norm of x. So this is very simple, and just write by taking n equals to 2, you will be able to prove it very easily. Yeah, so what we are saying is here alpha is 1. Right, the first norm should be less than or equals to alpha times second norm. Alpha is 1 here. So along with this exercise, what it says is that here we have x infinity is stronger than x1. Here we have x1 is stronger than x infinity. That means x1 and x2 are equivalent norms, right? Because one is stronger than other is stronger than the first one. So that means the convergence in one norm or infinity norm, that is same. Every sequence converges in one norm will automatically converge in infinity norm, and conversely every sequence converging in infinity norm will converge in the first norm. So topologically all these norms are same. But geometrically they are different. Why geometrically they are different? Because if you recall, we have drawn the unit ball of all these three norms, right? So in the Euclidean norm, the open unit disk is interior of the unit circle. In one of the norm, it was the diamond shape in the first norm, and in the infinity norm, it was square. So that is why the geometrically these norms are different, because unit balls have different shape. But as far as the convergence of sequence, every sequence converges with respect to either infinity norm or one norm or two norm, will always converge with in the other norm. So therefore convergence up to convergence, or that is as per the metric they are same, but geometrically the shape of the unit ball is different. Okay, so now we are going to use all these things to study certain results on for the continuous maps. So let us come back again to the continuity. In non-linear spaces. So whenever we have a non-linear space and we have a continuous function, we know that to check continuity we can use the the definition of sequential continuity. Right, so let's recall the definition. Okay, so let f be a map from x to y, where x and y are nonlinear spaces. We say that f is continuous f is continuous if, so the definition of continuity, if you recall, then that is xn converges to x in the domain implies the sequence fxn converges to fx in the codomain. Right, so first remark is that if the given function f is linear, then it is enough to check the condition for x equals to 0. So what does this mean? This means if f is continuous, then what is fxn minus fx? F is linear, so that is basically f of xn minus x. Right, so this condition is same as this one because f is linear. And since x is linear, if xn converges to x, if and only if xn minus x converges to 0. Right, so instead of checking the condition for all sequence xn converges to x, we will check the condition only for the sequences which converges to 0. Right, so therefore yn converges to 0 implies f of yn converges to 0 implies, so let us take yn defined to be xn minus x. Right, so if we assume this condition, yn implies yn converges to 0 implies fyn converges to 0, then just substitute this condition, we get xn minus x, that is yn converges to 0 implies f of xn minus x converges to 0, and that is nothing but xn converges to x implies fxn converges to fx because f is linear. So for the maps which are linear and which are from nonlinear space to nonlinear space, to check the continuity, it is enough to verify this condition. Alright, so that is meaning here that we need to check continuity only at the point x equals to 0. Alright, so for linear map, it is enough to check the continuity at x equals to 0. So the first result which we want to study, this result is also given in the, if you have read the book of Rudin analysis book. So in that book, this result is given as a map from Rn to any non-linear space. So if you have any map from Rn to any non-linear space, that is always continuous if it is a linear function. So proposition. The first proposition is that if the domain is finite dimensional, and we have a linear map f from x to y is a linear map. So whenever we have a linear map defined on a finite dimensional vector space, right? Of course, X is a vector space. Then such a map is always continuous. Right, so that is first result. Second result is that this fails if the domain is infinite dimensional. Right, so if X is infinite dimensional, then there exists a function f from x to y. So we can always construct such function which is linear, but it is not continuous. So first result says that if the domain is finite dimensional, every linear function is a continuous. But second result says that if the domain is not finite dimensional, then we can always construct a linear function which is discontinuous. Yeah, so in the second result, we need to assume Y is a non-zero subspace, right? Anyway, we are considering non-zero subspaces. So in the first part, we are going to use the finite dimensional vector space. So again, every time whenever we have a finite dimensional vector space, we have a basis and we have a coordinates. So yeah, so if the domain is a zero vector space, then F is a zero map. And zero map is always continuous. Zero map means it is a identically zero function. So that is a constant function and that is always. Yeah, so this is a trivial case, but in non-trivial case, that means suppose, so we are discussing the first part. Suppose X is a non-zero finite dimensional. So let's say vector space with dimension m. Right, so X has m dimension. So that means it has a basis. So let us fix the basis. So let y1, y2, ym be a basis of X. So now we want to show that f is a continuous function. So f is a continuous, we have already noted that to check the linear function is continuous, we need to only check it at it is continuous at origin. Yeah. So let us start with the sequence. So let xn be a sequence in X such that xn converges to some point X, right? It is enough to check for X equals to 0, but let us start with xn converges to X. So xn converges to X in X. So then every such sequence we know that we can decompose as coordinates. So kn1 y1 plus kn2 y2 kn m ym. Right. So basically, what is this? This is if we have a sequence of two coordinates. So what does this mean? This means we can divide as a sequence 1 upon n times e1 first coordinate plus 1 upon n square times e2. e1 is 1 0, e2 is 0 1. Right. So y1 y2 is this. So this is just an example of this decomposition. So now we have coordinate sequences, and of course x also we can decompose in this way. So k1 y1 plus k2 y2 plus mth coordinate km ym. Right. So xn converges to x implies each coordinate wise sequence converges. So knj converges to kj for all j is equals to 1 to up to m. Right. So each coordinate wise it converges. Now we want to show fxn we want to show fxn converges to fx, right? So for that, note that fxn is what? F is a linear function. So fxn is f of kn1 y1 kn2 y2 knm ym, right? So if we apply the linear function, the scalars will come outside. So that is kn1 fy1 kn2 fy2 knm fym, right? So now y1 y2 ym are basis element. They are fixed elements of x. So that means fx fy1 fy2 fym are fixed element of codomain, and then these are the coordinates. So we know that kn1 converges to k1, so that means this converges to k1 times fy1, right? Similarly, kn2 converges to k2, so that means this second element converges to k2 times the vector, right? And similarly, the last element converges to km times fym. And then if the first sequence converges to this number and second converges to this number, this plus this converges to this plus this, right? Addition of the convergence of sequence. So kn1 fy1 plus kn2 fy2 and so on converges to k1 fy1 k2 fy2 km fy1. And again f is linear, so that is k1 y1 k2 y2 km ym, because f is linear, so we can take scalars and addition inside. And then what is this element? This is a f of x, right? So you note down what is x. X is this element. So we just use f is linear here, and using that what we got is we got fxn converges to fx. Only thing we use is convergence of properties of convergence of sequence So xn converges to x, yn converges to y implies xn plus yn converges to x plus y. So this is the first part. So what is the first part? First part, we use that f is a linear function and we proved that it is a continuous. Because we proved that whenever xn converges to x, we have fxn converges to fx. Now the second part relies on the Zorn's lemma. So for the second part, what we have is we have a infinite dimensional vector space. Suppose dimension of x is infinite. So that means whenever we have an infinite set, it always has a infinite linearly independent subset. So this we mentioned earlier also. Whenever we have a infinite dimensional vector space, X has a infinite has a subset containing infinitely many linearly independent elements. Now these are infinite coordinates. So now suppose we have this L2, so that is a sequences of x1, x2, xn dash dash dash, so that summation of xj square is convergent. So now we have infinite coordinates, and then we know that if you consider E1, so E1 is what? 1 0 0, right? E2 is what? 0 1 0 0. These are infinite coordinates. En is what? 0 0 0 0 1 0 0. This is nth coordinate. So each of these E1, E2, En is a sequence. And note that the set En, n belongs to n, is a linearly independent subset of L2. So every infinite dimensional vector space, here L2 is infinite dimensional, it has a always infinite set subset which is a linearly independent. So such subset we can use to construct a continuous function. So what we'll do is we will first extend this set. So first of all, extend this infinite subset to a basis of x using Zorn's lemma. So we have discussed, when we discuss Zorn's lemma, we can extend every linearly independent to a basis B. Right. So here basis means it is a linear independent whose span is x. And then we can construct a function define fx to be y naught if X is element of the linearly independent set, and it is 0 if X is in the basis but not in L. Right? What is L? L is this infinite set as a subset L containing all linearly independent sets. So linearly independent set we can extend to basis, and the elements of L we are defining y naught. What is y naught? Y naught be a non-zero element in Y in the codomain. Right, so y naught should be other than 0. So it's kind of indicator function kind of thing. Right, so on this set its value is 0, on this set it is value is either 1 or y naught. So now we have defined this map on the basis elements, and once we have a function on basis element, we can extend it as a linear map. So that is a linear algebra technique that extend F to the whole set by linearity to get a linear function X. So first we define F on the basis element, and then we extended it linearly to the whole vector space, and then if we consider xn divided by n times norm xn, right? So what is xn? Xn is this set, the infinite set. So let L to be the set x1, x2, so on, infinite set. So these elements elements of L infinitely many, that will give us a corresponding sequence xn divided by n norm xn, and this is a unit vector xn divided by norm xn, but we are multiplying it with 1 by n, so this converges to 0. We already seen earlier, but f of this element xn divided by n times norm xn. So what is this? This is nothing but 1 divided by n norm xn times f of xn, and xn is element of L, so its value is y naught. Right, and this is non-zero value. So the sequence converges to 0, but this element it yeah, so here before defining fx, we are actually considering L as this elements, and then over xn is the fixed elements which on which we are, yeah, so this is a combination of y naught, so that is this element is non-zero. Yes, so therefore f of this element cannot convert to 0. So this gives us the idea that f is not continuous. Okay, so let me stop here. This is enough for today.